All right, so we're going to talk through what is happening during different stages along the titration of a weak acid, HA, with a strong base, sodium hydroxide. Notice that our weak acid, we're showing it being completely stuck together because weak acids, only a very small percentage of them ionize. So if we had maybe 100 molecules here in this picture, a few of them at any given point would be dissociating, but the majority of them are going to stay stuck together in their molecular form. So that's how we're going to show it. Our strong base, it's a soluble ionic compound, so it totally ionizes. So the sodiums and the hydroxides are separate. They do not stick together. So let's talk about what is going on in the beaker along the various stages of our titration. So right now we have pure weak acid, and the weak acid is going to dissociate. So there's this equilibrium happening where HA is turning H plus and A minus and going back. It's a weak acid, so its K value is less than 1, so we're not generating very much product. Okay, but that's happening. And if you're trying to figure out what is the pH of your weak acid, remember it's a calculation involving equilibrium. So what do? We set up a nice chart. And our K expression looks like a Ka, so it's products over reactants. And let's assume that each one of these particles represents 0.1 molar. So if I've got 4 of them, it means we've got 0.4 molar HA. Right now I have no H and A to start with. I'm going to use up some of my HA. So it's going to look like this. So we're going to have this general setup. We're going to end up with x squared over 0.4 equals Ka, whatever our Ka value is. And that's how we find the pH of a weak acid. Okay, so what happens as we start adding base? Well, the base is going to come along in here, and hydroxide is the best base that there is. So if you have any hydroxide ions around, they're going to come around and they're going to steal hydrogens from anyone else who's got one. So my hydroxide is going to come there and steal a hydrogen from my weak acid. So now notice I have weak acid, but I also have some A minus. And when I have a weak acid and I take away a hydrogen, the thing that's left behind is the conjugate base. So I have a mixture of a weak acid and a conjugate base, which means I have a buffer. And you will see this in your graph, that during this stage where you have some weak acid and some conjugate base, so it's after the beginning and before equivalence, you're going to see that the pH stays relatively flat. That's because you have a buffer, and so the pH is not going to change. So how does that affect our calculations? Well, if we look back here and think what equilibrium is happening, it's still the same equilibrium here. You still have some HA that's turning into A minus. Okay, you can also think of it as some of my A minus is turning back into HA, but that's my equilibrium. It's between HA and A minus. So I can still use my same equilibrium reaction here, still use the same K expression, so I can still use my Ka value. What's different though is instead of just having a value for reactants, now I have a value for reactants, which is 0.3 molar, and I also have a value for my products, which is 0.1 molar. And this is still going to be 0. We're still going to go through and do our thing with the change. And we end up plugging this all in your K expression. You end up with, what is it? Let's see. X times 0.1 divided by 0.3 equals my Ka value. So same equilibrium reaction. The only difference is instead of with all reactants, you have some reactants, some products. That's what makes a buffer different than a pure weak acid or pure weak base. So let's say we add one more base. This hydroxide is going to come in here and steal a hydrogen from my weak acid. And there's something special about this point. In this point we say we're halfway to equivalence, which means half of our original stuff has gotten used up. We started out with 4 acids, now we only have 2 acids left, and 2 of my acids have turned into weak base. So what's significant here is I've got equal amounts of my weak acid and its conjugate base. So if I think about what this looks like, so it's still a buffer, okay, but this is a special kind of buffer, and let's look at why. So when I plug numbers into my ice chart here, my HA is 0.2 molar, and my A minus is also 0.2 molar. And maybe you can see what's going to happen here. I'll fill this all out totally. 0.2 minus x, and this is x. 0.2 plus x. We'll assume that K is really small, so the change here is insignificant. So if I go through here and I plug this into my K expression, I end up with x times 0.2 divided by 0.2. So we should notice here, since the concentration of A minus and HA are the same, they cancel each other out. So what does that leave us with? It leaves us with Ka is equal to x, and remember x is representing our hydrogen ion concentration. And the significance of that is if you think about how we calculate pH, pH is the negative log of the H plus concentration. So if we take the negative log of both sides, the negative log of Ka and the negative log of H plus, we end up with pKa equals pH. So at this point, it's halfway to equivalence. It's the point at which your concentrations of your weak acid and conjugate base are the same. You're going to have a buffer whose pH is exactly equal to the pKa of your weak acid component. Okay, so this is a special point, halfway to equivalence. Now let's look at this thing we call the equivalence point. The equivalence point is basically like your endpoint of a titration, and that would be when you have used up all of your thing that's in your beaker. So I'm adding 2 more hydroxides. They're going to steal the hydrogens from the, where'd my other one go? From your weak acid. And notice at this point, you have used up all of your weak acid. You've made a bunch of waters, sodium ions are just hanging out. So all we have present now is just weak base. So this is another really important point along the titration, because if we look at this K expression we had been using up to this point, this is not valid anymore, because do I have any HA in my beaker? No, all I have right now is A minus. So we want to think about what the A minus is doing and what is the actual reaction happening here. So A minus is a conjugate base, so it's a weak conjugate base of a weak acid, and we know that bases are hydrogen takers. So what's happening is my base coming over here to my water, and it's going to be taking a hydrogen from water, making hydroxide. And this is going to be equilibrium, so it's going to be going back and forth. So we want to represent that with an equation. So let's write out a new equation, because it's not this that's happening anymore, it's something different. So my A minus is reacting with water, and when it reacts with water, it takes a hydrogen from water, making HA and OH. So that's my reaction. I can still, it's an equilibrium, so I can set up an ice chart, I can write a K expression. The key thing here is when I write out, if I take a look at this K expression that I have here, this is no longer a Ka expression, right? Because we're talking about the reaction of the conjugate base. So this is a Kb expression. And usually in this problem, you're going to be given a value of Ka. Like let's say they told you, okay, Ka is 1 times 10 to the negative 6th. And they probably won't give you a Kb value. You're going to have to figure it out. But that's okay, we can figure it out, because we know that when we're talking about a conjugate acid-base pair, the Ka of the acid times the Kb of the base equals Kw. So there we go. We can figure out Kb by taking Kw divided by Ka. And if we think about the reaction happening here, now I have 0.4 molar, let me put this back over here because it's mostly going to stay in this form, 0.4 molar A minus, we ignore water because it's a liquid, and this is 0 and 0. And notice this setup looks exactly like what we had in step 1, right? So if we look back at what happened in step 1, like before we added any base, we had 0.4 molar weak acid, and we were using a Ka expression here to solve for pH. At equivalence, now we have 0.4 molar weak base, and we're using Kb to find pH. So the tables have turned here. It's just important that you make sure you acknowledge like what is present in your solution and which reaction is happening here. Also, point out, we have been assuming that the volume of the solution does not change. So that's why we start out with 0.4 molar here and we end up with still 0.4 molar at equivalence. In real life, if you think about what happened during your titration, it probably took maybe 20 mils of base in order to neutralize your 20 mils of acid. So this concentration is actually going to be diluted. So when you go ahead and do this at equivalence, you're going to expect your molarity to be less than what you started with. So like maybe it's going to be around 0.2 molar. And you'd have to look at the specifics of your reaction, look at the volumes that are given to figure out what the true molarity is. But just know at equivalence it's going to be a little diluted compared to your starting point because you've added some volume to your solution. Looking back at, let's backtrack a little bit and let's take away a couple of sodium hydroxide and look here back at this point where we had a buffer. So initially, if it's pure weak acid, you have to use this reaction. If it's pure weak base, you'd have to use this reaction. If it's a buffer, you could use either reaction and it would work out. So we were showing this, like let's say we're at this stage. So let's think about this buffer scenario. I could use my acid dissociation and say, okay, I have 0.3 molar, I've got 0.1 molar HA and 0.3 molar A minus, and I could set up my chart this way. Or I could use this reaction, and I could say I have 0.3 molar A minus and 0.1 molar HA. And either setup that I use, I'm going to end up with the same answer. And if that seems weird to you, remember this is a Ka and this is a Kb, it all ends up working out. So when you have a buffer, you could use either reaction, but if it's pure weak acid, you have to use this reaction. If it's pure weak base, you have to use this reaction.